I'm just going to repeat this again. I probably have to repeat it for the next few weeks. All my assignments are now on Canvas. There will be a new one for next Tuesday. I'm also starting to put up solution sheets, so if you have questions about the homework, the first thing you might do is look at the solution sheet. And then if you still have questions, you can come see me. If you feel like there's some question, like maybe I got something wrong on the solution sheet, or you think a lot of people in the class would have trouble with a problem, you can bring it up at the beginning of class and we can go over it. All right. Okay, anything else before we go onwards to math? Math, all right. So, last week, at some moment in the class, I had this impression that I put some trigonometry on the board, and a few eyes may have glazed over, and so I thought it would be worth a really quick review. I'm not going to do all of trigonometry, but some things I think you should know for this class. You're going to run into little stumbling blocks. They're not calculus, they're trig. So we're going to start just with this kind of diagram that should be fairly familiar to you. This is a unit circle. We have an angle here, which we'll call theta. And we divide up the circle into 4 quadrants, which have names, they're labels, 1, 2, 3, 4 in Roman numerals. Around the edge, I list some angles in degrees and radians. You should know all these conversions. I mentioned a few specific angles, 30, 45, 60, 90, 180, 270. You should know the value of the trig functions for all of these numbers. If you don't know if it just doesn't pop into your head, you should have a way to figure it out pretty quickly. As an example, if you're dealing with 30 degrees, well, the right angle is a 30, 60, 90 right triangle. And the ratio of the sides you should be able to get from geometry. This is 1, this is a half, and this is square root of 3 over 2. And from here, you should be able to figure out the sine, cosine pretty directly. For 45 degrees, 60 degrees is just the I want to say conjugate, but that's not the right word. Supplementary, complementary. It's just the complement. Now, as you get an angle out beyond 90 degrees, you run into the issue of the SIGN of the trig functions. Sine, cosine, all the trig functions are positive in the first quadrant. In the second quadrant, you can see the sine stays positive because it's the y-coordinate still above the line, but the cosine and the tangent become negative. As you get around to the third quadrant, sine and cosine are negative, tangent is positive, and so forth. You should know these things pretty well. You should, if you don't know them, like 1 plus 1 is 2, you should at least be able to look at this and think about it for a minute and figure it out in a straightforward manner. So that's the most basic trig stuff. There's a lot more really basic stuff that I'm not gonna go over, but I'm gonna focus on a particular particular area, which are identities. Now, the first few things I'm going to mention should be really obvious, and depending upon who you talk to, they're not really identities, they're definitions. But, we have the tangent, I'll put in a theta, is the sine of theta over the cosine of theta. Secant of theta is 1 over the cosine of theta, and the cosecant is 1 over the sine of theta. And if you're like me and you like things orderly, you have to kind of burn a little hole in that orderliness, because the cos don't correspond, right? So the cosecant 1 over the sine. I'm sorry, the secant 1 over. See, I did it wrong. Oh gosh. Secant, cosine, cosecant, sine. Yes, okay, I did it right. You have to kind of burn that in because it's kind of asymmetric. They could have named them differently, but I'm sure there's a good reason. Okay, so these are basic, we'll call them definitions. Then the next most important thing is going to be the Pythagorean identity, which comes up all over the place. Sine squared theta plus cosine squared theta equals 1. And even though, in class the other day I showed you how this comes from the theorem, with a triangle, it doesn't really matter where you are in the circle. You can't really have a triangle with 270-degree angle, but this holds up no matter what. This thing isn't falling off. That's the problem. Okay. There are what I will call the odd even identities. Someone here know what an odd function is? Yes? You're onto something, but that's not what we use the term odd function to mean. If you said the odd degree polynomial, that would be correct. But I'm looking for something different. Yes? Symmetric with the origin. So that would be symmetric if I drew it right, like x cubed, symmetric with the origin. Yeah, that's right. We have a simple definition you can always use, which is if f of negative x is equal to negative f of x, then we have an odd function. And one of the prototypical odd functions is going to be the sine, right? If you look on both sides of the origin, right, everything is off. Everything is switched. So then we have an even function. Can anyone either give me the definition or an example? I see you know. I'm hoping someone else will throw up their hand. Yes? Half of negative x equals that what you're saying?
No. F of negative x. Like the function of negative
F, so you're saying f of, and I'm seeing half. I'm hearing half. F of negative x, thank you, equals
f of x.
f of x, yes. That's the definition. Any function that this is true of is even. Now, functions are not necessarily even or odd, but some functions are even or odd. Can someone give me an example of an even function? Okay. X squared, that's a great one. Now, you can look at it this way. You can say, well, if I plug in f of negative x into x squared, I get x squared. Yeah, that's f of x. That's one way. In others, you can look at the graph. The graph is symmetric around the y-axis, then it's even. If it's symmetric, again, as was suggested across here, across the origin, it's an odd function. All right, so little detour there. So we have sine of negative x equals negative sine of x, because it is an odd function. We have cosine of negative x equals cosine of x. Now, from there, you can pretty much figure out the rest, right? Tangent of x, well, let's say tangent of negative x is obviously sine of negative x over cosine of negative x. But sine of negative x is negative sine of x. Cosine of negative x is still cosine of x because it's even. So we just have negative tan of x. So that tells me immediately the tangent is an odd function, right? Cotan is just the reciprocal. That'll be odd. Secant negative x is 1 over, well, you can kind of see this coming, cosine of negative x, which is 1 over cosine of x, so, which is secant of x. So the secant is an even function, and the cosecant will be an odd function. Again, if you graph any of these, like here's cosine. Again, if it's symmetric around the y-axis, it's an even function. Okay. I wanted to say a little more about the Pythagorean identity. Nothing particularly startling or astonishing, more useful, right? I can very simply manipulate this as 1 minus cosine squared theta equals theta, or, alternatively 1 minus sine squared theta equals cosine squared theta. And the utility of this is when you're trying to simplify something or manipulate it, you might run into these expressions, these, and then if you recognize these, immediately you can simplify it. In addition, you may have a sine squared, a sine or a sine squared, and you have an equation that's got a bunch of cosines, and if you could make them all the same thing, you could solve for it. So sometimes you want to convert, a sine into a cosine. Now, if you're careful, if it's not sine squared, if it's just a sine, you can still get away with this. You have to be careful because this might be plus or minus. You might have to think about, when is it plus or minus? Does it work either way? But you can sometimes do that kind of substitution. And this, to me, is all, it's all the Pythagorean identity. All right. Any questions? You could give me a hand where this means, I know this already, or this means, wow, this is all new, or that was okay, that was an okay review. Can we have everybody kind of give me a... Okay, all right, so I don't want to blow anyone away, and I don't want to waste your time. I think this is just a few more minutes of this. All right. Now we get into the stuff that's a little more advanced, that's going to, again, come in useful in calculus. We're going to start here with the sum and difference formulas. Sine of A plus B, which turns out to be sine of A cosine B plus cosine A sine B. So we have the some sum here, but we could express it in terms of the individual functions. If I change this to a minus, well, you could figure that out by plugging in minus b here. Well, minus b here does nothing, right? Cosine of minus b is cosine of b. But sine of minus b is going to be minus, so this would become minus. So we sometimes will abbreviate it this way. Sine of A minus b is all this minus this. All right, that's it. That's an important identity, important formula you should know. We have a similar one for cosine of A plus b. It's cosine A cosine b minus sine A sine b. Similarly, if you want to know what the minus is, it becomes a plus here. And you can do that same trick with the odd even functions, substituting them in. And, a lot of these things are connected. So you'll see, you could memorize them, or you could memorize just the important ones and put them together. The actual proofs of these, if we were in a trig class, there's a beautiful, beautiful geometric proofs of these. They're kind of fake because they involve triangles and they really just have to do with the first quadrant, but then you can extend them. All right. And from these, you can find the sum and difference of all the other trig functions. For example, tangent of A plus B, well, that's going to be sine of A plus B over cosine of A plus B. All right, so we have to write all this stuff out here. Sine A cosine B plus cosine A sine B over cosine A, cosine B, minus sine A, sine B. Now, that already gives you the formula in terms of sines and cosines, but usually we want to write this in terms of tangents, so we need to find a way to turn it into a tangent. So the way we do that is we divide both sides by cosine A, cosine B. I'm just going to slip in there cosine A. I can do it that way. Cosine B. And then we just have to look at what we've got. Well, sine A, cosine B, cosine A, that's just the tangent of A. Same thing here, we divide by this and we get sine B. Oh, that's just the tangent of B. Over here we have 1, and over here we have what? Tangent A, tangent B. So you can, once you know the basics, you can, if you kind of have that feel about it, you can derive the other formulas. Like these, there's a plus or minus here. You make this a minus, well, you get a minus here and a plus here. Did I do that right? No. Plus should be down here. So tangent of A minus B is tangent A minus tangent B over 1 plus tangent A tangent B. Again, it's a choice if you want to memorize it or you just want to know how you can get to it. I'm just going to erase this and move this up. Okay, so there's some less general formulas that are probably more useful. If I want to know the sine of 2A, well, that's just the sine of A plus A. So that tells me it's the sine A cosine A plus cosine A sine A. So that's just 2 sine A cosine A. The thing to recognize is that this comes up quite a bit, sine A cosine A. So if you see it, you can just think of it as sine of 2A over 2. That'd be like a substitution that might come in handy in a calculus problem. Cosine 2A, there's a little bit more to it. Again, if we just plug in, we'll see it's cosine squared A minus sine squared A. But this reminds us, these sine squares and cosine squared, remind us again of the Pythagorean identity. And there are two other nice ways to write this. You can write this as 2 cosine squared A minus 1. That's by substituting in, wherever I have it. Oh, I don't have it anymore. Well, sine squared equals 1 minus cosine squared. So if I plug that in here, I get 2 cosine squared A, or I can write it as 1 minus 2 sine squared A. And these are tricky looking little expressions that if they show up, it's really good to know, oh, you can trace them back. I'm just going to leave, I'm just going to write down the tangent here. We don't have to go through figuring it out. You could just substitute in yourself. And the last place I want to go with these, because you can just follow through, is the half angle formulas. So if I had sine of a over 2, well, I have the sine of 2a here. That's equal to this. If I was to substitute here for 2a, just a, I'd have sine of a equals, I'm not really sure if I'm doing this right, I just thought it'd be useful to know, cosine a over 2. Oh, so now I have an expression for sine a over 2. Is this going to get me where I want to go? I don't know. This has to be square root of 1 minus sine a over 2 squared. You know what? I shouldn't have gone here. I'm going to do a proof. I should at least head in the right direction. I should at least know what I'm doing. I'm just going to write these down. You can look up, in your pre-calc book, or if you want to come to office hours, make me work. That's fine. It's just plus or minus the square root of 1 minus cosine of a over 2, or the cosine of a over 2 is plus or minus square root of 1 plus the cosine of a over 2. These will tell you the tangent, right, as a square root, but you can also write the tangent of a over 2 as sine of a over 1 plus cosine of a, or 1 minus cosine of a over sine of a. If you want to know how you get between these two, try multiplying this one by 1 minus cosine a over 1 minus cosine of a, and you'll get a Pythagorean identity simplification. Okay. All right, that's all I have on trigonometry. Is there any questions? Again, if you're weak, you might want to brush up a little in this area. There are going to be a lot of problems with sines and cosines, and at some point you may need to simplify them, modify them, use your knowledge of identities. Okay. Just want to catch up here. So, Devin, got some homework. And did I miss anybody? Oh. Tell me. This is one of those. You're Lero. Yeah. Okay. All right, I have something for you. Okay. All right. What time is it here? It's 10:30. I think we're going to take a break, quick break now, and then we're going to come back. We're going to do the chain rule. It's kind of a meaty subject. So take a few minutes. stretch, relax. Come ask me questions. Bugs me that I don't remember how to do this, so let's see. Oh, of course. Of course. This is off the record. So, cosine of 2x is cosine squared x minus sine squared x, which is equal to 1 minus 2 sine squared x. Right? Wait, is that what I wanted to do? Yeah, oh, no. Yes, that's right. So we've got cosine of 2x equals 1 minus 2 sine squared x. So I switch these and I get 2 squared x equals 1 minus cosine x over 2 or sine x, 2x equals plus or minus square root of cosine 2x over 2. So that's just from the cosine of 2x. But if this is x and this is 2x, I can just make this x over 2, and I can make this x. Okay. That's how you do those. The interest level is all right, are we all back? I think so. Anybody? Okay, we've got 2 absences. All right. We've been spending a few days looking at these different rules to help us do differentiation. We have, the sum rule, product rule, quotient rule, the power rule. These are all pretty useful, but nothing that we're going to learn is as useful as the chain rule. If you've seen it before, good. If you haven't, you have to practice with it a little. After a while, you get the feel of it. And it's just really super at taking all sorts of ugly, complicated functions and giving you a direct route to find their derivatives. The chain rule specifically has to do with dealing with finding the derivative of the composition of functions. So if, for example, I have some function f of x, and I have some function g of x, and I make a new function, we'll call it h of x, which is f of x, g of x, and I want to find the derivative of h of x, I can do it in terms of the derivatives of f of x and g of x using the chain rule. Let's take kind of a real example. We'll just say f of x equals the square root of x, and g of x equals x squared plus 1. So f of g of x is the square root of x squared plus 1. Now, I guess in a way I'm doing this backwards. You're usually not like given f and g. You might. Usually you're given some ugly construction like this that we don't know how to find the derivative of this. I mean, you might guess, well, squared x squared is x. So maybe it's like the derivative of x. No, that doesn't seem plausible, right? But we can break it up by treating it as a composition of functions. We're going to see this written out in two different ways, using both the Newtonian and the Leibniz notation, and both actually have their own place where they're more useful. So you'll see. However, they are both interchangeable. So the way the Newtonian notation looks, f of g of x, or f of g of x, is equal to, well, the derivative of it is equal to the derivative of f at g of x times the derivative of g at x. Okay, we'll get into exactly how to interpret that in a minute. With a Leibniz notation, you're usually thinking of like y equals f of x, or y equals, let me get this right. Well, in my example, it would be y equals h of x, which is f of g of x. And so we make y equals f of u, and then we have u equals g of x. And the very kind of nice, pretty way we write this is we say the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. So in both cases, this multiplication is the same multiplication. All right, let's apply this to this function here. The derivative of f of x, that would be 1 over 2 square root of x. You can just use the power rule. So the derivative of f of x at, g of x is 1 over 2 times the square root of g of x, which is x squared plus 1. Well, that's the first half. The second half, if I want to add the second half, it's just going to be this again. But now we have to find the derivative of g of x. Well, g prime is just 2x. So times 2x. And here we have a simplification. We can eliminate the 2 and we'll get x over square root of x squared plus 1. That's how you apply the chain rule. Now, before I go any further, we're going to do a bunch of examples. You're going to have a chance to try it out. I don't want to do a proof of this because it would be kind of obscure, and I don't think you're going to get much out of it. But I want to see if I can make this idea seem plausible with an example or two. So the first example I want to do is really simple. I'm just going to say f of x equals x and g of x equals x squared. Now, let's think about that in terms of a graph for a second. I've got x, that's just a straight line, a diagonal, and x squared is going to be a parabola. So f of g of x, well, as I said, this is going to be a simple example. It's just going to be x squared. And we already know the derivative of this. It's 2x, right? But let's go through the step here. The derivative of f of x is just the constant 1. So f prime of g of x, well, it's just 1. F prime of g of x times g prime of x, well, we know the derivative of g of x is just 2x, so it's just 1 times 2x. So it turns out in this trivial case, of course, it works. You're merely multiplying the derivative of f of x at the function times the derivative of the second function. All right, now that's so simple. I don't think it's quite enough. I want to just go one step further, do something a little more complicated to see if it, again, maybe to give you some physical intuition. Why would if you have a composition of functions, why would you multiply their derivatives? That just seems, it doesn't seem obvious. All right. So let me try something just a little more complicated that we already know the answer to, but let my f of x be x squared, and my g of x also be x squared. So my composition, f of g of x, will just be x to the fourth. Well, we know the derivative of that from the power rule. That's just 4x cubed. So that's where we're going to be heading. But let's do it the long way around. Let's use the chain rule. So we want to know what f prime of x is. Well, that's, of course, 2x. F prime at g of x. Well, now I have to plug in x squared here, right? G of x is x squared. So that's going to be 2x squared. That's just the break alarm. Okay, one more. F prime of g of x times g prime of x. Well, this is 2x squared times the derivative of x squared, which is 2x. And what do we get? 4x cubed. Just kind of what we knew the answer had to be. So again, it seems like a trick, but in fact, this seems to be the way you get the derivative of a composition of functions by multiplying these derivatives. All right. Now, what we really haven't gotten to is how powerful this can be. Let me take what I think should look like a pretty imposing looking function. H of x equals e to the x cubed. I mean, we know e to the x, we know x cubed, but we really don't know what to make of that at first sight. I mean, we definitely don't want to go back to our definition, right? H prime of x is e to the x plus h cubed minus e to the x cubed over h, and then find the limit as h goes to 0. That would be painful. So we break this up, right? We have f of x equals e to the x, g of x equals x cubed, and then we just go through our chain rule. So derivative of f of x is e to the x. The derivative at g of x will just be e to the x cubed. And then what's g prime? It's 3x squared. So f prime g of x, g prime of x is just 3x squared e to the x cubed. Wow. I mean, this is pretty ugly, and this is even uglier. But there it is. That's our derivative. All right. Two more examples from we'll call it the land of trigonometry. I'm just going to skip some of the steps here. First thing I want to know is, what's the derivative of sine squared of x? Well, this is, you start looking at this and you start thinking, well, there's function x squared in there, right? And we're plugging sine into that x squared. So what do we do with x squared? It's just 2, whatever was in there, sine of x. Just like x squared, sine squared 2 sine of x, but because of the chain rule, now I have to multiply by the derivative of the sine, which is cosine of x. Okay, now, hearkening back to the beginning of class, does anybody recognize something here? Because we have a really nice simplification here. right? Sine of 2x is 2 sine x cosine x. Okay, so that's the derivative here. All right, let's try something that looks similar but is completely different. What about sine of x squared? Now we've got the composition of two functions but going the other way. Before it was sine and x squared, now it's x squared and sine. Okay, we look at this, we say derivative of the sine is the cosine. Of what? Well, x squared at x squared. Now we have to multiply by the derivative of x squared, which is just 2x. Or if you prefer, 2x cosine of x squared. A little practice and these things will become very smooth the way they work. As long as you, like in your head, you already know the derivative you're dealing with. If you don't, you have to stop and calculate it separately. But again, these become very straightforward. Okay, now I want to focus on something here. Why is this called the chain rule? Where's the chain here? Well, in the examples we've had, we've just had the composition of two functions. But there's no reason we couldn't have the composition of three functions. We could have h of, I don't know. I don't want to write it that way. All right. G of h of x. Well, the Newtonian version of that looks kind of ugly. It's going to be, the derivative is going to be the derivative of f at g of h of x times the derivative of g of h of x. Well, what's that? That's the derivative of g at h of x times, now we have to multiply again by the derivative of h of x. The Leibniz version looks much nicer. Just say dy dx equals dy du times du dv times dv dx. You have to set up the u's and the v's to be the functions properly. All that said, why did my alarm go off at 11? I have no idea. That said, all this is actually more complicated than the implementation. So I'm going to put forth here, again, a rather imposing looking example. All right, so we have to break this down. Let's call, because it's a polynomial, we'll call And we're finding the square root of it, right? So that can be our g of x. All right, so here we have g of p of x. That's our square root. But finally, we're raising this to e to the x. So our f of x can be e to the x. So we have to find each of these derivatives. This one is going to be e to the x. This is, so this is 1/2, so 1 over 2 square root of x. And this is a polynomial with the power rule plus 2. So our first step, f prime of g of p, well, this is g of p here, so at g of p is just going to be, that's the nice thing about e to the x. It's real easy to find the derivative, right? It just doesn't change. Now we have to find the derivative of g prime at p of x. Well, where's my g prime? So that's going to be 1 over 2 times the square root of what we have in here. And finally, p prime of x, I guess we already showed that. That's 3x squared plus 2. So combining this all, we have the derivative is e to the square root of x cubed plus 2x plus 1 times 1 over 2 times the square root of x cubed plus 2x plus 1, and finally times the last derivative times 3x squared plus 2. Now, when you're doing these, you're going to find you have a comfort level with some and not with others. In some, you might want to write all this stuff out, but you could just look at this and say, well, I know the derivative is just going to be e to the square root of x cubed plus 2x plus 1 times the derivative of this guy. Well, that's a square root, so times 1 over 2 times the square root of, carrying this along, times, the derivative of that. That's not that hard, 3x squared plus 2. I mean, as you get practice with it and as you get comfortable with it, it will get smoother. You'll see more of them, and you'll have a sense of them. So with that in mind, let's get a little practice. If you have some paper handy, I guess I'll leave this up. Let's take a few minutes, and again, don't be intimidated by the fact you haven't seen one just like this before. Let's try and think it out. E to the sine squared 3x. Let's find the derivative of that. Tony, is this yours?
No, that's not.
No. Who am I I'm confusing you with someone. I think I'm confusing you with someone who dropped the class. Calvin. Is this yours? You're Calvin, okay. Yeah. Okay, sorry. Is this hard? I'm just asking. Is this hard? Okay. Would someone like to try this on the board for us? Not even for a caramel Lindt irresistibly smooth milk chocolate truffle? All right. I shouldn't be teaching bribery, should I? Trying to make the world better. All right. All right, let's someone at least tell me what the first thing I'm going to write is. Derivative of e to the sine squared 3x. What's the first thing I want to write? Yeah, thank you. Just rewrite it. They won't all be like this. Okay, now I've got to multiply it by something, right? This is now gone. Derivative of sine squared of 3x. So you got to think of the power rule here. Power rule is usually dealing with x, a function, right? Here it's sine of x, but that's okay. Because we're doing composition of functions, right? So what's the derivative of, writing down the answer, of x squared? It's 2x, but the x here is sine of 3x. So we have to multiply it by 2 times the sine of 3x. Okay. We're not quite done. Now we have this new function, sine of 3x. So what's the derivative of sine of 3x? Well, again, the function here is sine, right? So what's the derivative of the sine? Cosine times the cosine of 3x. We're almost done, because the derivative of the cosine of 3x sine of 3x is not the cosine of 3x. It's the cosine of 3x times, again, so we have a function in here, 3x, we need to multiply by its derivative. Okay, this is using the chain rule 3 times. Okay, but you notice I didn't have to take my pen off the board, or right? It takes a little while. All right, let's try one that looks a little different. Still going to have an e to the x, but now I just want to say, I know that there's this instinctual reaction when one sees big numbers like 5 to panic. So, remember that advice from the Hitchhiker's Guide to the Universe. Don't panic. It can't be all that bad. Again, we've got a function like x to the 5th with some stuff in it. All right? Well, why don't you work on it for a couple minutes? Okay, anyone want to suggest where we might start? Yes, Lillian? It's not your fault. Try again. Stop right there. Excellent. Everybody catch that? There's some function, we're composing a function, but there's some function in here, x to the 3x, e to the 3x plus 5, 5x squared to the 5th. But we can just use the power rule on that. It's not an x, but it's a function. So 5 to the 4th, that thing. Yeah, okay. All right. Very good, Lillian. Someone else want to tell me the next step? In general, what do I have to do next? I have that function. Right? I have to use the chain rule. I have to multiply by its derivative. Well, there's 2 pieces to it, so that makes it a little more complicated. But what's the derivative? So now, in isolation, the derivative of 3e to the 3x plus 5. What's the first part of that? This is the easy part. We're going to find the derivative of this whole thing, but just this part right now, we're adding this. E to the 3x plus 5. What's the derivative of, what's the first part of that I'm going to write down?
Oh, well, yeah.
You're too quick. You want me to multiply by the derivative of this, right? Somebody else. What's the derivative of 3x plus 5? Okay. All right. So that becomes this, and then we have this. What's the derivative of 5x squared? 10x. Oh. It's messy. In some problems you might need to simplify a little, but that's it. All right. If you're not getting it, just pay attention. See if you can get the rhythm of this. There's kind of a rhythm to it. All right. New problem. This one, just so you have exposure to it, I'm going to do it as using the Leibniz notation. I'm going to say y equals 3u squared plus 2, and u equals 1 over x minus 1. So you can think of this as y equals 3 1 over x minus 1 squared plus 2. And here we have dy dx is going to be equal to dy. This is just our formula. Du times du dx. And let's look at these. Well, y equals 3u squared plus 2. So its derivative is what? Derivative of 3u squared plus 2 with respect to u is just what? That should be pretty simple. This is just the power rule. Nobody? I know it's just a few minutes before lunch and blood sugar is at the low, but, you know, imagine you're at the end of the, yes, thank you. Where am I? 6u, yes. We'll worry about what u is later, yeah. Yeah, 3u squared. Well, what the derivative of u squared is 2u, so times 3, it's just 6. Right? Du dx. Oh, uh-oh. Let's write this as x minus 1. We're going to use the chain rule on this. You'll never have to do it again. You just be obvious. What do we do? Minus 1 times this. I want to find the derivative. Minus 1 times x minus 1 to the minus 2. But now I still have this function in here. I have to multiply by its derivative. The derivative of x minus 1 is 1. Yeah, so we don't have to do anything else. So, okay, let me write this down. It's minus 1 over x minus 1 squared. And now, to make it look pretty, I should plug in for u. So u was 1 over x minus 1 times minus 1 over x minus 1 squared. And, okay, I can simplify that a little further. page of these. We're not going to get through all of them, but let's have some fun here with this. Okay? Now, here's an example from the book of Don't Be Intimidated by Big Numbers. They're just there to scare you. So, f of x equals x squared, oh, that's not a big number, to the 100. Oh, I got the 100. Oh, will I be here all, one way to solve this, the wrong way, well, it's not wrong, it's just ridiculous. You can multiply x squared minus 1 times itself 100 times, and you just have a polynomial, right? That would be, and then find its derivative. Yeah, you could do that. Now, we have a composition of functions. We have a function x squared minus 1, and then we're taking that to another function to the 100th. So, how do I do this? What's my first step? It's just like if it was 5. Except it's 100. I see you have the answer. Is there somebody who hasn't answered before who wants to stick their neck out a little? Maybe? All right. He stuck his neck out first. I'll let you answer. Yeah. Power rule, yeah. Well, help me out. What do I write? 100. Okay. And we're almost done. We're almost done. We're not quite done. What's the next thing I have to multiply it by? Derivative of x squared minus 1, which is 2x. This chain rule it's fantastic. It lets me do things that, I couldn't, I'd be a heavy weight lifter, I couldn't do them. All right. All right, let's pull out all the punches here. Let's do something that it's not interesting, but it's hard. All right. That's my f of x, and I want its derivative. So, again, don't be scared. Just go at it. What's the first step I'm going to do? Work on it for a minute. See where you go. Once you get the swing of this, the calculus isn't hard. It's the algebra. Right? Yeah. When I do my homework, which I have to do, and I do a problem, I have a big stack of paper that, I used and just on one side, so I have lots of scrap and I can just scribble all over it and throw it away if it comes out wrong. And I'll just do these over and over again until they look right. You want to do it carefully. Now, when you're taking the exam, if you want scratch paper, let me know. I'll bring in all that you need. You have to be careful. That's all. Okay. Someone want to give me a hint? The first step here? It's the same as the last step. I see you have the answer. Is there somebody? I see Lillian has the answer. Is somebody else want to stick their neck out here? It won't get bit off. Emily? Thank you, Emily. Excellent. Okay. Oh, to the 3. So I'm not done yet. Now I have to find the derivative of what's here. What am I going to do? What am I going to use for that? Use a quotient rule, right? So let's see if I can do the quotient rule without a mistake. Derivative of f, this is f and g. Derivative of f, that's just 3 times g, x squared plus 1 minus 3x times the derivative of x squared plus 1, which is 2x. So this becomes x squared all over x squared plus 1 squared. Okay. Man, is that ugly looking, but it's a function. It's a derivative. There's some simplification you could do here, but I don't think we want to worry about that now. All right. I don't know if anyone else feels this way. I'll try not to spend too much time on it because maybe it's boring. But I always find it interesting that you don't have to do it one way. You could do it another way. So in particular, let's look at x to the 4th plus x squared plus, no, that's not it. X 4th plus x squared plus x squared. And I want to find the derivative. And let's say I don't know the chain rule. Well, I know the power rule, and I know how to multiply polynomials. So x to the 4th plus x squared plus x times x to the 4th plus x squared plus x. Okay. X squared, x cubed, x to the 5th, x cubed, didn't leave room, x to the 4th, x to the 6th, now I have x to the 5th, x to the 6th, x to the 8th. All right. Someone catch something? No. Okay. X squared, 2x cubed, x to the 4th, 2x to the 5th, 2x to the 6th, 2x to the 6th, x to the 8th. All right, power my way through this. 8x to the 7th plus 12x to the 5th plus 10x to the 4th plus 4x cubed plus 6x squared plus 2x. Okay, I did it without the chain rule. What's my first step here? Same as we've been doing the last two problems. Use the power rule on this whole thing. Right? 2 times x to the 4th plus x squared plus x times the derivative, x cubed plus 4x cubed plus 2x plus 1. So now all I have to do is see if I get the same thing. Well, I'm not going to check everything, but I will look at this. 4x cubed times 2x to the 4th is, what do you know? It's 8x to the 7th. Funny, it still doesn't look right, but I'm not going to check any further. Oh, there's a 2 here, yeah. Oh, I see. So 2 times x plus 2x, yeah. So the 2 on the end are right. You can go in and check to see if the others are right. They better be. They will be if I did it right. If they aren't, try again. Okay. I see a problem here. It interests me. It's a chain rule problem, of course. 1 over x plus 2 minus 1 over x minus 2. Now, you can just go at that. And I have something tells me that's probably the right way to do it. Just go at it the way we've been going at these. But does anyone look at that and think, maybe I should try something first before I start finding the derivative? Anyone have any thoughts on that? I mean, sometimes, problem you can get at it 2 or 3 ways, and one of them is really, really hard, and lots of algebra and lots of room for mistakes. Sometimes there's an easier way. I'm going to do the power rule, and then I'm going to do either, if you like the quotient rule or the reciprocal rule on these guys. But I'm looking at this and thinking, it's like they're asking me. Aren't they asking me to put these over a common denominator? I want to try that before I do anything else. So what do I have? I've got x plus 2 over 1 times x minus 1 over x minus 1. Oh, minus 2 plus, minus 1 over x minus 2 times x plus 2 over x plus 2. So down below, I've got x plus 2 times x minus 2 is x squared minus 4. I have x minus 2 minus x plus 2. So I'm going to end up with minus 4 over x squared minus 4 cubed. I didn't do any calculus yet. I just found the derivative, and I'm thinking, well, maybe this will be easier. I don't know. Let's see. So I have 3 times minus 4 over x squared minus 4 squared times what? the derivative of minus 4 over x squared minus 4. So what does the quotient rule give me? Well, the derivative of 4 is 0, so forget that. Minus the derivative of this, which is 2x times minus 4 over x squared minus 4 squared. Okay, so I don't know. It wasn't that hard to do it, but it looks kind of ugly. What happens if I try it this way? 1 over x plus 2 is 1 over x minus 2 to the second power. Now I have to find the derivative of these guys. Well, I think we saw earlier, this is just x plus 2 to the minus 1, so its derivative is minus 2 times x plus 2 to the minus 2. And then minus, we're going to get the same thing here, minus 2x to the minus 1 squared, so these go away. I think my intuition turned out wrong. I think it was like easier to just go through it. But, you know, you don't know unless you try. All right. There's a homework assignment on Canvas that involves using the chain rule. You can get started on that if you wish, but we may do a few more problems on Thursday, just because I think this is, to me, this is the most essential skill you will learn in this class as far as finding derivatives, which is the most essential skill for the class. Okay. Okay. No homework. Anyone want homework? Just want to turn in? Okay.
Yeah.
Good. Thank you. Thank you. Yeah. Drop them down.
Thank you.
You are welcome. Thank you.
I got a question about this.
Please do.
Because like, so I wrote it out like, I'll write it on like this.
Do you also have a question about this one?
Yeah, because I think the forward's wrong.
Yeah, I saw.
Yeah, because like it's like this. So that's the question. 1 over x plus 2. Then minus 1 over x plus 2. So I rewrote that into like that bracket minus.
That's good. Yes. Yeah.
And then if I did the derivative of this, I should get something like, so do the outside first. I ran out of space. Then you times that by,
Yeah, you know, you got it. If it's different,
No,
if I made a mistake, it's because I'm, you know, stupid.
Yeah, it's like you roll -2 instead.
Oh, I wrote negative.